This is the first time you come to this. Yeah, I'm a third year. I finished my Ochem on second year, 128. I think it's very similar to 118. Wow. Like Ochem. Um, it's not that hard. I think it's pretty interesting actually. Um, like it's does not involve a lot of like maths, but I don't hate maths. But I just like the things like I think Ochems are using imagination of how things go here and go that way, and there are a lot of memorizations in the future. You may not like it. You do like memorizations a lot. Yeah, it's a way to understand it. Yeah. Why there's a... Okay, I think it's time now. I will stop the song. Wait, stop. So today is a one-on-one. Oh my God. Like, okay. Like, we're just going through last class, we talk about gyro centers, and a little bit review, but this is the first time, so this is not a review for you. Like for how we define a gyro center is that a gyro center will have four different things connected to it. So this is a glucose. Okay. Well done. We have another person. Hi. Hi. Yay, we have three. We're just starting. And a little bit review of yesterday. I bring little model kits. You guys can sit here. Yes, we don't have a large group today. Yeah. So, just going through a little bit from yesterday, we learned what is a gyro center and how to determine the S and R configuration for gyro centers. So today I bring a little glucose here, and then the definition of a gyro center, it's a molecule that is connected to four different things. For example, in this molecule, we have this. It's a gyro center because it's connected to four different things. Yeah, this is a different group. A different group. So, like, these two are the same thing because they're exactly the same. They're two hydrogens, and for this one, it's connected to one, two, three, four different things. So this is the gyro center. And for this one, this is not because it has a double bond connected to the oxygen. And just because last time we're all doing this through imaginations, so this time I'll bring this, like, we can try one. Like, for example, how about this carbon? Like we want to determine its S or R configurations. Like for the step we're going to go through is to label them one, two, three, four. So just to expand it, we label it from the one is the biggest atomic number. So so from here we can see that oxygen is the biggest atomic number connected to this four. This we label it one, and then hydrogen we label it four because it's the smallest atomic number. And then the way we compare this, these two groups, this one wanted have a try to compare these two groups. Like we did it last time. Yeah, this is a double. Yeah, so this one is bigger than this one. So the way we wanted to do is compare the biggest atomic number and number it. This is 1, 2, 3, and 4. You can ask questions because you're not here that time. No, the way we compare it, I will go a little backwards so that we're just doing some reviews because I bring a little model here so that everyone can go through a little behind here. So we're comparing like this. The For example, for this So, um, let's go back to this gyro center. So we number it 1, 2, and 3, and the hydrogen is here. So which S or R do you guys think is this gyro center? This one is 1, 2, and 3, and 4. It's hydrogen is over here. Yes, R because it's gray. Yeah. Then how about we go another one, like, how about we go this one? This one. So this one, hydrogen's in front. Okay, this is 4. This is, what do you guys think this one is? Yes, it's 1 because it's a oxygen directly connected to this carbon. And then we want to compare this two. So first, these 2 carbons, we have oxygen, oxygen, hydrogen, hydrogen, carbon, carbon, same. So we move on the next carbon. So we're going to compare this 2. It's just connected to 2 oxygens, 1 hydrogen, and this one, 1 oxygen, 1 carbon, 1 hydrogen. So this one is bigger than this. So 1, 2, 3, and 4. But this time the hydrogen's in front. Wait, 1, 2, 3. Yes. Great. So I think everyone gets that. And for the Fisher projection, I want to bring this in so that everyone can see how. Oh, and for last time, someone asked about the meso compounds. So the definition of meso compound is that there are achiral compounds that has multiple chiral centers. So for example, this one is a meso compound, and that one is also a meso compound. And then for the Fischer projection we go through last time, this is a glucose, and this is also a glucose. I want to show you guys how it draws like that. So we want to put it, so this is the double bond O, put it here, and then but it's not 3D active portion. Yes. Also going to learn this in Ochem class. Okay, and now we're going to go through some new things. So Newman projection. Okay. So the Newman projection is a way of drawing like molecule, like a way to present a molecule. Like for example, for the first one, we see from here, we wanted to put it like this. We see it from here, and then we compact it into the Newman projection. So this is what the Newman projection is. So we have a front carbon and the back carbon. So the front carbon, we just draw the lines out, and for the back carbons, we draw a circle and 3 little short lines. Yes. So, for example, like back to our glucose. For this one, we want to draw a. This is too. Okay. For this one, we want to draw a Newman projection. We just look it on this side, and then so this is the front carbon, and this is the back carbon. So for this, we just want to draw. It's like the front carbon. We have a OH group here, and hydrogen here, and for the back carbon, this is a broken thing. So this is just R group and a hydrogen down here. and the OH group here. OH. So this is how you draw the Newman projection. Okay. So this is the front carbon and back carbons, and so yeah. Also, you can draw it actually from front and from back. Actually, problems with that. The problem is tell you which way are you going to draw from front. For example, these are the drawing problems questions for Newman projection. So for the first one, for A, we see it from this side. So this side is the front. This is the front carbon. This is the back carbon. And so front carbon, we have 3 methyl groups. So methyl group Me, Me, Me. And then for the back carbon, we have a Me and 2 hydrogens not drawing out. And then for B, here are some wedges and dashes. We want to draw the wedge and dash correctly. So for this case, we cannot draw like A, just randomly put the Me's and H's. From this, I want to draw the chlorine here because it's pointing outside and you're looking this side. And we have a hydrogen here, a carbon here, and then this will be the chlorine because it's pointing inside of the screen. We're looking this side, so it's on the left. And then the carbon will be here. Oh, the carbon is Me methyl group, and the hydrogen will be here. Okay. And also, we can go through F. This time we're looking at that side, the different sides. So this will become the first carbon, and this will become the second carbon. So the way we draw this, the Cl will be here, the Me will be here, and the H will be here. And the bromine will be here, the Me and H. Get it? Okay. So you guys can, let's say, work on E. Try to draw. So let's go over E. So this is the first carbon. This is the second carbon. So the first carbon will have chlorine and EH, and the second one will have chlorine H. H. I don't know what. Okay, and the Ne here. So we're not going through C and D. You can look at it. On the right side, C, the CLs. Because you're looking at in this way, so it will be on your, yes. Do you guys want to go practice C and D? Who want to do practice? Okay, let's do C. Okay, let's go through C. So this is the front carbon, this is the back carbon. We want to draw these have two carbons on here. I'm gonna call it a like acyl group. Acyl group is called ET. You can abbreviate it like this. Okay. Yeah, it's also okay. For we can put it like one carbon, two carbons. Yes. And then for this methyl group, it's pointing this way. So here, methyl and a hydrogen. And we have one carbon, two carbons, acyl group here, and then two hydrogens. Okay, so let's go to the steric hindrance and energy of Newman projections. So we can see we have two confirmation of Newman projections. Like for the first one, all the hydrogen is not, for example, we can do this. For the first one, like they're not hiding each other from it. So you can see every atom's in front. But the second confirmation, which is exclude confirmation, you put it like this. So you cannot see everything in the front. For the first staggered confirmation, the energy will be low and this will be more stable because like the atom's not bumping into each other. They have their own space, like and the 60 degree is the most stable one, and which is called the staggered conformation. And for the eclipse conformation, everything is bumping into each other, so it's not very stable and cause a very high energy. So here we have a energy diagram here. We can see that all the staggered conformation has a very low energy, but the eclipse conformation has a high energy. And then we can also change group putting on them. So for example, now we have a methyl group in the front carbon and a methyl group on the back carbon. So this is the NT position, which is the most stable one. Like the two big groups are not bumping into each other, they have their own space. But for this one, it is a staggered conformation, but there are two huge groups bumping into each other. So we can find it here. It has a low energy, but not the lowest one. So this one will be the lowest one. And if two huge groups exclude together, it will be the highest energy and the most unstable one. Yes. And now we're going through the cycloalkanes. So we'll talk about the cycloalkanes on the first class about how to name them. So here we have a lot of cycloalkanes. The first one is cyclopropane. It has 3 carbons, and etc. So, but however, we can see that the cycle with 3 carbon is very unstable. We have a very high energy because of the bond. Like, you can see it's very hard to put it like this. It will tend to break. And we also can see that 6 and 12 is the most stable one. So we will see a lot of 6 carbon rings and 12 carbon rings in like natures, for example, glucose. Yeah. Okay. So how does a 3 carbon ring look like? And why it has a really high energy? Like we can see this is a Newman projection for a 3 carbon ring. It is excluding everything together, so really high energy. But so 4 and 5 carbon, it does not sit in the plane. They wanted to move up a little bit so that they do not eclipse together. So 4 carbon and 5 carbon looks like this. And here is the most important one, which is the 6 carbon ring. We have a lot of conformations here. We can see we have chair, which is the one with the lowest energy. We have half chair. We have boat, twist boat. For a chair, this one is actually a chair conformation. If you look at these 2 carbons, they're not hiding the back carbon. You can see everything in here. So it's a staggered conformation. It will be more stable. But for the bold conformation, we can see that the 2 carbons have a eclipse conformation, so we will have a high energy. Yes. Okay. So the boat is here. Okay. And also for the 6 carbon rings, we have the A bond XL bond and equatorial bond, A bond and E bond. So from here, we can see that all the A bonds is the one I put the hydrogens on. And all the E bond is pointing out, it's pointing outside. Like they're pointing outside, and all the A bonds are pointing straight forward. And also, we can do a ring flip. So I can change all the A bonds into E bonds and all the E bonds into A bonds without breaking this molecule. So I just do this. So that everything changes over. Like the hydrogen now is printing outside, and this ones are printing straight forward. So this is a ring flip. Like every molecule, the six bond, like six carbon rings can do it by itself. Like, and we don't have to add some heat or something. They're just going to happen. Okay. So when they ring flip, the A bonds turns into E bonds, and the E bonds turns into A bonds. So now let's try to draw a chair conformation. So for drawing a chair conformation, here are some tips. So we can draw two parallel lines, and then another two parallel lines, and then connect these two together. It will be a chair conformation. Yes, the biggest. And then when it's ring flipped, you just draw it in another way. So you draw the parallel lines in this way, and then another two parallel lines, and then connected this two. And now we want to try to put this chlorine and methyl group onto our chair conformation. So for this one, the chlorine is facing up. So we wanted to put chlorine here. And then the methyl group is facing down. We want to put the methyl group here. So this is chlorine, this is methyl group. And then if we reflip it, this carbon will be here. And then it would turn into a equatorial bond. And then the methyl group will also turn into an equatorial bond. So in this way, we can see that actually this arrow is going to be like this, because we want the groups to be on the equatorial bond so that it does not react or bond into other atoms. Okay. Yes. And here's the exercise. You can go ahead and try it.
assume that the heaviest group goes to the equatorial position. And then if that one's on the equatorial, then the Winston strands, it has to be on the axial position.
Yes, they have to be like one up and one back. Okay. So for this one, we want to draw this one, we put it on this carbon, so it's pointing up. It's an A bond, and then 1, 2, this one was on the equatorial bond in here. And if we flip it, this will be the ET, and then the ME will turn into an A bond. Yes.
Yeah, I didn't officially know where to put it on that one. Where like what I was trying to get at is why can't you put the
Essel?
yeah the ethyl group
Actually, it does not care. Does not matter if you put it in. Oh, put it in here. And so if you put it in here, that methyl group will be here. And then if you ring flip it, this carbon will be here. So this is ET. And the Me will be here. So actually it does not really matter where you first put the acyl group. And this one is like it looks harder, but actually you can just think of that as an R group. So where do you want to put? How would you like to draw it into a chair conformation? You can go ahead and draw it. Try. So for this one, um, for the for the Fisher projection, we have a front carbon and the back carbon. This one will be the front carbon for this Fisher, and this one will be the back carbon, front and back. So we'll draw it like this. So the OH group, we'll put it here. And I will ignore all the hydrogens. And this R group, we can just cut R. It's in the A, like A bond. It's very easy to transfer Fisher projection into chair conformation. So this is the same molecule that is on the last page. So we want to recognize it from each of the projections we learned. Okay. So if we have a ring flip of this molecule, what did you guys think the OH group will be and the R group will be? Yes. So the OH will, the will be here, and the R will be here. So the stereokindrons, just like what we are talking about, like we want to put big groups, not heavy group, but big groups on the equatorial, and small group on the A bond. So if we have a meso group here, it will tend to be in this position. Okay. Um, so it is not the heavy or light one. We see that like it's like the big or small, and we have a chart for it. You can look through this chart and determine which one will be more bigger and which one will be more smaller. So we can do some practice. This is a very simple one. Compare which one is more stable. Compare which one is more stable. The left one or the right one. Yeah, because it's on the E bond, and the right one's on the A bond. Okay, but sometimes we have the trans, like the trans conformation. So we want to determine which one will be on the A and which one will be on the E. We want to look at this chart. So chlorine is very small, and it is a 70 to 7 to 3 ratio of A and E bonds. So, and we can see the acyl group is here. It is a 96 to 4. So actually, in this case, acyl group is bigger than the chlorine. So we want to put the acyl group on the equatorial and the A bond. So we can draw it out. This is the ET and 2 over here. Cl and the ET and Cl. So it would prefer this one. Yes. Okay, now we have an exercise. Like compound A exists in the chair conformation, while compound B exists in the twist bolt conformation. Can you explain that? I want to show you like the twist bolt conformation. It's here. So twist bolt. To that question. Yeah. Yeah, so compound A, it will be O on the equator. Is okay. So we can draw it out. Like it's correct. For the chair conformation for compound A, we can draw it like this. No, but you will not have chance to draw it. This is just this question. You can draw it like this. You connect it. Wait, this is not very clear.
More stable that way compared to the state confirmation.
Yeah, it is more stable because it's on the like the E bonds, the R groups and R groups is pointing outside, not this side. Yes. And then for the A bonds, one up and one down. It will all be on the equatorial bond. And then this is the glucose one. So the glucose actually it can go from linear to cyclo, from cyclo to linear. Um, you will learn this in 118B or 128C. Yeah, they're the same. And then for the glucose, how do you put it into a six ring? Because no six carbons, there's oxygen there. So I'm just gonna go through this. So this oxygen is going to attack this carbon over here. So you want it to connect this attack here, and then the oxygen, the hydrogen will connect to this oxygen. So now it turns into a six ring glucose. And then here's a problem for you guys. Like there are alpha D glucose and beta D glucose and alpha D glucose. We can see that the ratio is not exactly the same. So you guys can go ahead and try to explain why the beta D glucose is 64 and that one is 38. You can try to draw out the chair conformation for both alpha and beta and see like which one might be more stable. No pressure. Can go through. We can. Yeah. one on the A bond. Yes, I can draw it out so that everyone can visualize it. So we draw a chair conformation here. And then draw, actually I want to draw it this way. So oxygen is here. So OH, 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 OH. And then for the alpha, OH, 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 and then, so you can see the only difference is here when it's a equatorial, when it's a ACO bond. So that
if we say that if there's like the second we see it, you see that there's two different same conditions. That we can assume that the other one is happening more often because it switches it. If it is possible to move carbon apart and have it all in the position.
different size? Yes. Like, you can think like that. It'll be more fun. And then we have one last practice. This is a weird one. So this molecule is tend to be like this. So it's on the ACO bond, not the equatorial bond. Why do you guys think it's like this? The hint is we have oxygen and hydrogen. Between hydrogen and oxygen. Yes. So in this molecule, we just have two hydrogen bonds. Like we can form hydrogen bonds here. So this way, it's on the A bond, not the equatorial bond. Yes. And then this is the conclusion for last class and this class. We talk about isomer, enantiomer, diastereomers, and Fischer projection. Today we'll talk about Newman projection and cycloalkane. And then, as we know, we're a little bit behind for our schedule. We're like in here, but we're already at class 3. So I'll keep up a little bit, or maybe I would keep chill and let everyone to understand all the things. And then for next class, we're going to learn how to draw Renaissance structures. Okay. We're good.